Can you know who wins before anyone makes a move? Take a number string 5 blank, 4 blank, 9 blank, 1 blank. Split it down the middle and two players take turns filling those blanks in. One wants the two halves to add up the same, the other wants them to end up different. Do you really have to play out every possible sequence of moves to know who wins? Alice and Bob take turns filling in the question marks in a string of digits, with Alice going first until every question mark has been replaced by some digit from 0 to 9. Bob wins based on how the final sum of the digits works out once the string is complete. This one's LeetCode 2029 Some Game. I'm Kai, and this is Fun with Learning Technology. You are given a string of even length made of digits and question marks. On each turn, a player picks a blank and replaces it with any digit 0 through 9. That keeps going until every blank is filled. Bob wins if the first half and the second half end up with the same digit sum. Alice wins if they don't. Both play as well as they possibly can, and we need to know, before a single move happens, who actually wins. Take the string 2, 5 blank blank. The left half is 2 and 5, summing to 7. The right half is just 2 blanks empty so far. Alice fills one of those blanks with a 9. Now the right side already holds 9 by itself, more than the left 7, and there's still one blank left for Bob to use. He can drag that back down to equal, so Alice wins this one. The string length is always even, so the two halves are always the same size. No awkward leftover character. It can be up to 100,000 characters long, which rules out anything that tries to simulate every possible sequence of moves. And every character is either a digit or a question mark, nothing else to worry about. The instinct is to just simulate the game, try every digit, 0 through 9, in every blank, in every order, and see who wins. Take a string with just 6 blanks, that's already 10 to the 6th, a million branches to search through, and this problem allows up to 100,000 characters. There has to be a shortcut that never touches the game tree at all. Forget the two sums separately. Track just one thing, left sum minus right sum. Bob wins if he can force that difference to 0. Alice wins if she can force it away from 0. Say Alice fills a blank and changes the difference by some amount. It looks like you now need to track magnitudes, like a stone game style value optimization problem, because that's the shape people default to whenever a game involves picking numbers. But you don't, because digits only run 0 to 9. Whatever value Alice puts down, Bob can always pick a digit in the other half that cancels that exact shift, so the cancellation is guaranteed, not something Bob has to search for. That's what turns this into a pure counting problem instead of a value optimization one. As long as both halves still have blanks left, Bob can always mirror Alice this way, so mid-game moves are a wash, they don't decide the outcome. After all that cancelling, only two things actually decide the game. The difference between the two sums right now, and how many blanks sit in the left half compared to the right. The specific digits players choose along the way don't matter at all. This is where the mirroring trick from a moment ago actually pays off. If the blanks split evenly, Bob can mirror every move Alice makes, pairing digits so each pair sums to 9. And that only breaks down if the starting difference is already too big to close. If one half has strictly more blanks, Alice gets extra moves Bob can't match, and she drags the difference wherever she wants. Bob only wins the tie when the blank counts match, and the existing digit sums are already equal. It's tempting to stop right there and say whichever half has more blanks, that player's opponent just wins automatically. But take a new case, 1 blank on the left, 3 on the right. That's uneven, and Bob still wins it. 2 of those 3 right side blanks can pair up with each other, and Bob can force that pair to always add up to 9, no matter what Alice picks. Only a genuinely leftover, unpaired blank hands Alice free control. First, split the string right down the middle. Count how many question marks sit in each half, and separately add up whatever real digits are already there. If the total number of blanks is odd, Alice always wins outright. Somebody ends up with one free, uncancelled move. Otherwise, Bob wins only if the existing difference exactly matches 9 times half the gap between the two blank counts. Let's put the whole thing together. We open with a class, solution, and a method called SumGame that takes the string and returns a boolean. First, we find the halfway point and slice the string into a left piece and a right piece. Then we count the question marks in each piece and separately sum up whichever digits are already sitting there, ignoring the blanks. If the total blank count is odd, we return true immediately. Alice wins. Otherwise, we return whether the existing sum difference is not equal to 9 times half the gap between the two blank counts. The odd blank check catches the case where mirroring can't cover every move. The 9 times comparison is just Bob's pairing trick from earlier, written as one number. This runs in linear time, since it's just one scan across the string. It uses linear space too, because slicing makes copies, though you could trim that to constant space with a manual loop instead of slicing. The bigger pattern shows up anyway. Two players alternately push a shared quantity toward or away from a target, drag the running difference, and the move counts on each side, and the winner usually falls out of one comparison instead of a search. Talk is cheap, let's actually run this. I fed it all 3 of the problem's real examples, no cherry picking plus 3 extra edge cases I picked myself. Let's actually time both on a real 10 element input. Brute force took 851 microseconds. The optimal version took 24 microseconds. That's a real 34 times from actually running both just now, not a complexity estimate. Here's one for you. Alice picks 25 ? Can she always force a win no matter what Bob does? Pause and take a guess. Think about who has more blanks to fill before you answer. Yes, Alice wins here. She holds both blanks, so she decides the final parity herself. And that's the whole game. Second one. If Alice and Bob each get exactly one blank, who comes out ahead? Guess before I say it. Think back to why equal moves tend to cancel each other out. It's a tie. With one blank each, their moves cancel out in pairs, so neither player can force the parity their way. We solved LeetCode 2029, some game, figure out who wins when Alice and Bob fill in blank digits to make two halves sum equal or unequal. The whole game collapses to one question. Is the number of blanks odd or even? Because every move Bob makes can cancel out Alice's move in pairs, except when one is left over. That single parity check replaces simulating the game, giving own time and O1 space.